All right, hey everybody, welcome back. So we just finished talking about why we would care about moving forward with studying orthogonal sets of vectors. And then we discussed how orthogonality actually implies linear independence, provided none of the vectors in your set is the zero vector. But let's continue on the first theme of why we care about studying these sets in the first place. And maybe the question doesn't seems like it's this question doesn't seem like it's going to be terribly important for the moment. But notice how we can set up the following question in terms of a familiar problem. So suppose we have this basis, right? And we're just trying to figure out what are the coordinates associated with a given vector with respect to this basis. Right, it's a standard question. I mean, we asked this in first semester linear algebra, and it turns out to be kind of an interesting question. It turns out to have an interesting answer. That for these arbitrary bases, the question of constructing the components of this vector, and just so we understand what I mean here, so that this C vector downstairs, it's going to be the weights that I have to attach to the V vectors in order to produce W. Okay, so this is exactly what I mean in that notation. Nothing more, nothing less. Whee. And one more. Yeah, one more. So if we are looking for the weights, right, the weight vector C here, that produces this vector W with respect to the beta basis, we actually have to set up a particular equation, a particular set of equations. So if we were doing this in terms of, I don't know, maybe the basis is 1, 1, minus 1, 1, minus 1, 1, and minus 1, 1, 1, right? So this would be our set, our beta set here. So this is beta. And we're trying to produce, say, the 1, 1, 1 vector. Then what we actually have to do here is ask, well, what weight do I have to attach to this vector, and to this vector, in order to produce the W vector, which was 1, 1, 1. And you can see very, very quickly, we get C1 plus C2 minus C3 has to be 1. And then C1 minus C2 plus C3. And minus C1 plus C2 plus C3. And we see very quickly here that this can boil down merely to a question of how do I solve a system of equations quickly, right? How do I solve this for the weights C1, C2, and C3? So in particular, what winds up happening in general, we have to solve an AX equals B system. And that's exactly the setup I have over here in this equation. Right? That's all that we're doing in answering this question, and we want to be able to do this quickly. If I circle all of that, I can kill it off at the same time. Look at that. All right. So if we want the coordinates of a vector, we're going to have to solve some version of the linear system AX equals B. Maybe orthogonality is going to help us figure out how to do this more quickly? Yeah. Probably not, or maybe it will. We'll find out. So we showed before that this would naively take on the order of n squared or possibly n cubed computations, right? N cubed would correspond to Gaussian elimination or naive Gaussian elimination. And n squared we talked about using an LU factorization to use forward and backward substitution to solve that. But for orthogonal bases, we actually don't have to do too much work at all, as it turns out. So if we are fortunate enough to have constructed an orthogonal basis, or even an orthonormal basis, then we can compute the coordinates of a vector readily, just by using the inner product. And this is what we're going to show downstairs here, that if we were to give ourselves an orthonormal basis, right, very, very important that we're using an orthonormal basis here, then we could express the coordinates of an arbitrary vector w as just the vector of inner products of w against each element of the orthonormal basis. And this, honestly, is one of the easier computations we can make. They're just dot products, in effect. And when you throw this into MATLAB, that's exactly what you're going to get. It's going to be some weighted dot product. So standard dot product will take you, what, on the order of n? Yeah, it's an order n computation. So we could conceivably get our computation down to order n to compute these these coordinates, rather than going to n squared or even worse, n cubed. So let's see about how this works, and it's really not too bad. Right? All these orthogonality questions, all these theorems about orthogonal sets, is going to boil down to how can you compute an inner product, or what happens when you compute the inner product against an arbitrary vector. And if w here is indeed equal to some linear combination of these u vectors, then we can go ahead and invoke linearity again, so we can separate out the sum. So this sum comes outside, and all of these coefficients come out in front, and they can also, in fact, not just out in front, they can come all the way outside of the inner product as well. And we wind up with almost an identical computation to our linear independence proof from last video, where the only thing that's going to survive here is the case where the index I matches up with the index j. So in particular, we can go ahead and say that the Cj weight is exactly just this inner product on the left-hand side. That's just the inner product of uj with the arbitrary vector w. So no problem. This actually shows us how easy it is to use these orthonormal bases. And if we were to go ahead and continue, right, let's see if I do that on the next page. I totally do. We can actually see a generalized Pythagorean theorem out of this, right, where we say that the length of the vector is exactly the sum of a whole bunch of squares. Notice how we're not using the dot product anywhere in here, right? This is an abstract, arbitrary inner product. So we get something that looks like the Pythagorean theorem for our standard Euclidean inner product space, but it's for an arbitrary inner product. But the thing that makes it work is the fact that we have an orthonormal basis to play with. We've given ourselves something that looks like the standard Euclidean basis. All right, and once we've established that we have the orthonormal basis, then we take the dot product of v of w with itself. And again, it's a matter of how do these guys combine to create a whole bunch of zeros, right? So we see in this computation, right, we're invoking bilinearity again to show that we're going to wind up with a delta ij, right? And that's going to tell us that the only time that we don't have a zero in this computation is when I equals j, which would make a ci squared in the final computation. And that's exactly what we set out to prove, that the square norm here is exactly the sum of the squares of the weights. And we've already shown what the sum of the squares of the weights looks like. That was this guy right here. All right. So we get a generalized Pythagorean theorem. Now, let's come back to that original question. How do we compute the coordinates of an arbitrary vector here if we have an orthonormal basis? Well, it's just going to be all of these inner products. And we're doing this, for example's sake, we're doing this on the standard R4 inner product space. But the idea is that all I have to do to get the coordinates, these w beta coordinates, is going to be some c1, c2, c3, and c4 vector. This will be exactly the inner product of u1 hat with W, not W1, just with W. And then the second component, U2 hat with W. Then U3 hat dotted with W. And the last component, U4 hat dotted with W. And all four of these computations can be done, all four of these computations can be done readily, and I do that here on the left to show that, sure, this coordinate vector is actually very, very easy to compute. It's this guy right down here. Just throw all the dot products into one vector. And that tells me that I can go ahead and use those weights to represent this vector. So W, this is what, 4, 1, 1, 0, right? This is exactly that vector there. Can be computed from these weights down here. Right? There's a -1 that goes in front of the U1 vector, a 2 that goes in front of U2, a 2 in front of U3, and a 3 in front of U4. That's how much of each vector I need in order to construct W. Okay? So having that dot product, or having that inner product there with an orthonormal basis, actually makes this computation near linear, if not linear. And we can double check that the weights here, right, if I'm taking the inner product of W with itself, I'm going to get the square norm of the vector W, right? So I can go ahead and check real quick. Sure, that there's 4 squared plus 4 squared plus 1 squared plus 1 squared plus 0 squared. That will give me, what, square root of 18? But that's exactly the same thing as taking the square norm of this coordinate vector in the standard R4 inner product space, right? -1 squared plus 2 squared plus 2 squared plus 3 squared is still going to give me a root 18. Okay, so we can use the weights to give ourselves the lengths of the vectors, right? And we can do that without solving an entire linear system, which is kind of a godsend for us from a practical standpoint. Okay? Now, continuing this a little bit, we can go a little bit further. What happens if we don't have an orthonormal basis? Well, it's still not terrible. It's not ideal, but it's still not a terrible computation. If we have an orthogonal basis, but we don't have unit length basis vectors, then the only thing that really changes in this computation is that we have to scale down a little bit. Right? We just have to scale down by a tiny bit. Right? So in the computation from before, right, it's the same proof, or the same work in the proof, right? So we can go ahead and factor out, there should be a CJ in here as well, shouldn't there? No, because I'm just doing that against UJ, not against an arbitrary W. Right. So again, invoking bilinearity, or just linearity in the second component of the inner product. This dot product UJ, or the inner product UJ with W, can be seen as this CJ times the length of J squared, or the norm of J squared. Right? Again, that's because this term in here becomes a Kronecker delta. Right? So once we have that delta in place, we can get rid of a lot of computations. And that's exactly what we expect to do, or what we hope to do in this computation, is that we see that the weight Cj can be solved for by taking the inner product and dividing it by the square length of the basis vector uj. And that's exactly this formula down here for the weight. Right? And that's what we have right up here. Okay, so that's what the theorem is saying, that we are just going one step further in the generality and saying that, well, if we don't have a unit length or a normal basis, then we're going to have to scale down by the length here, just by a little bit, just to make sure we're not over lengthening these vectors or overweighting them. And very similarly, all we have to do to establish the Pythagorean theorem in this setting is the tiny little bit of algebra here at the end, right? We already know what Ci has to look like, and we can notice that this cancels with 2 of the 4 length of ui components downstairs. and we combine them into a single square term at the end. Right? Not too bad. It is just a little bit of algebra. But again, once we have the orthogonal basis, we can still compute these coordinates. So if I go back as an example to our original example sitting in R3, right, this guy up here, and let's say I wanted to figure out how, or figure out the weights or the coordinates of this arbitrary W vector sitting in R3, then I can go ahead and compute the inner products, just these three guys, like I did before. But the problem is that W is not going to equal -2 times U1 plus 4 times U2, and that'll be minus, not plus, minus 8 times U3. And you can check this, even just in the first component, right? Something, something, plus 4 times 0, something, something, minus 8 times minus 5, something, something, right? Even just in that first component, we wind up with, what is that, -2, so what? 40 minus 2 is a 38. And that's definitely not going to equal W, because this guy is supposed to be a 1. I did that right? It looks like I did that right. Okay. Cool. So we definitely have the wrong scales in mind, and this is exactly what these square norm bits are going to do for us. They're going to scale back the coordinates so that we have the correct weights. Okay. So I have to take this ratio, right? So for C1, I'll have to take U1 with W and divide by the length of U1 squared. And that turns out to be a -2 over a 6. So it's a -1/3. So that is the appropriate weight that I have to put on U1 in order to construct W. And very similarly, I'll have to take the ratio between U2 dot W with U2 norm squared, and the same for the third vector U3. Right, and when all the dust settles, we wind up with this collection of weights. And there we go. We wind up with that collection of weights. And you can verify that this is indeed what we get, or what we have to do to create the W vector with the orthogonal basis U, or beta, I suppose. And we can double check that all of these different, we can check that all these, or the length squared of this guy, of this W vector, is going to be exactly what happens when we square up not just those components, unfortunately, but just their numerators, really. Why do I have a -2 there? Oh, that's why I have a -2 there. Yeah, because I'm going off of that bit. There, okay. Not simplifying stuff. That's okay. But all I'm doing is I'm squaring those components and dividing by the square lengths of their respective vectors, and you can verify indeed that gives me the length of the vector, which was 6 from before, or √6. So it'll give me the square length of the vector. And we still have our Pythagorean theorem. Right? It's just got to scale it down a little bit. Okay. Now, I think the last example we will do, yeah, so let's do the last example. We'll do this in the not so familiar space, right? So this is what I was saying in the previous video, that we're going to go ahead and take a finite dimensional space sitting inside an infinite dimensional space, and then work with a basis on the finite dimensional space. So we can check the inner products between these three vectors, right? They're kind of contrived. I made sure that they were orthogonal. I had to modify the monomial basis in order to make that happen. And we'll show you how to do exactly that in the coming videos, something called the Gram-Schmidt process. But I digress. You can verify. The inner product of 1 with x minus 1/2 computes as 0. Hooray. Inner product of 1 with this third vector, x squared minus x plus 1/6, again, is going to give us a 0. Hooray! And the last one, please, oh please, did it work? Did it work? Yeah, you're going to have to do a little bit of algebra here. Sorry, not sorry. Right, you're going to have to do a little bit of algebra to show that this comes out cleanly. Quarter plus a third minus a half minus a 12th. And again, that will give you the 0. So indeed, this is an orthogonal basis for P2. Whee! There we go. Get all those little dots out of there. Come on. Sweepy sweep. Get out of there. Then, not the for, then for f of x equals x squared, right, we're going to do the same thing. We're going to think of this as the w vector from before, and we're going to try to construct this guy in coordinates based on that basis beta. So the theorem tells me that I have to compute the inner products of all three of these guys with x squared, right? And I can do that pretty quickly, right? I've done Calc 2. I know how to integrate stuffs. Polynomials most of all, right? So these are the inner products that you will wind up with if you compute against the basis. And then you still have to compute the square norms of each of these vectors, which again isn't terrible until you get to the last one here. So it's the FOIL problem from hell. I'm sorry. No, I'm not. So what we have to do then to compute these coordinates is to take the ratios between the two. So in this case, this was 1 with, with x squared divided by the length of 1 squared. And this is exactly the computation from above. So it's the 1/3 divided by the 1. Okay. Very similarly, I'm going to have to do what? It's x minus 1/2 against x squared against the length of x minus 1/2 squared. And that's the 1/12 over 1/12 that we see. There's the 1. And last but not least, we also pick up a 1. Phew. Not as terrible as it seems. Especially if you can have a computer do all these inner product computations for you. I wonder how we can make that happen. And as a final note, let me make sure. Yeah, you know what? We can save that? No. Where do we stop? Yeah, this is the last little bit of the section, so I'll end on this, this example here with the Fourier basis. So in homework, right, it was actually an extra credit problem, right? Last time I taught this class, it was an honest-to-goodness homework problem. But without an inner product space, showing that this collection of functions is linearly independent is actually kind of difficult. You have to know your trig identities very, very well, and then make a very strong argument as to why that set is independent. I think the easiest way I know how to do, how to show that is through sampling. And you wind up talking about the Nyquist frequency. It's just, there's a lot to this problem, but if you have an inner product space, the problem becomes almost trivial. Notice that this set, we can show that this set beta, what do I call it, beta k, is actually an orthogonal set, right? And that's what this computation is. I'll let you look at it on your own here, but you can show that these vectors, these functions, are all mutually orthogonal to one another. And our theorem says that if you have an orthogonal set where none of the vectors are 0, then your set is linearly independent. Okay, and we can go ahead and go one step further and scale these guys down by the appropriate square norms, and we wind up with an orthonormal set. And in the proper context, we talk about beta infinity here, where we include all integral frequencies of sines and cosines. This is, in some sense, a basis for periodic functions. Right? This is called the Fourier basis. Right? It's going to be a cornerstone of many, many applied linear algebra algorithms. Or in signal processing, you'll use this. In tomography, you will use this. In just about any application you can think of, there is a way for you to use Fourier analysis. It's kind of amazing. And we'll talk about it some more, and you will explore it further in a project. But for right now, let's go ahead and end